All right, 2.7, inverse of a function. Now, the inverse of a function, f at x, is denoted by f inverse of x. So what you have is f with a little -1 of x. This, folks, is not an exponent, so very important to note. Now, to find the inverse of a function, you can do one of the following things, depending on what you're given. Number one, you can interchange the x and y coordinates in the graph or table. And if you do that, that will give you the inverse coordinates. If you're given a graph, you can take points on it and just inverse them and draw the new shape. If it's a table, switch the x and y coordinates. That's all you're doing. Another way is to take the graph that you're given and reflect that graph in the y equals x line. That means that there would be the inverse coordinates would be mirror images of the original coordinates. The last possible case is you can interchange the x and y in the equation and then solve the new equation for y. Now keep in mind, y is not really y, but the inverse. So I usually highlight it or identify it in a different color to remind myself it's the inverse and not the original y value. So we can do that, and I'm going to show you some examples of all three of these in the following slides. Here we go. Before we do anything, we have to remember a couple of things. For algebraic inverses of quadratic functions, the function must be in vertex form. So folks, if you're given the quadratic in standard form, you will be required to convert it to vertex form. That means, yes, that dreaded completing the square. You may need to review some completing the square before you continue. Now, the inverse of a function is not always a function. And this is important because when you take it and reflect it across the y equals x line, you're going to see an example of where the function is, the original is a function, but its inverse is not. Now, in order to make the inverse a function, you must restrict the domain of f at x to make the inverse a function. And we're going to see an example of that really defines how to restrict the domain. Last part, the notation for inverse is f with a -1. F with a -1 of x. So this is how you write inverse. Very important though is that this means f inverse of x and not that it is an exponent. It is not an exponent, folks, so cross that out. No way. It is not an exponent, okay? F with a -1 of x means f inverse of x. All right, moving forwards. Example 1. Find the inverse, f inverse of the function. So inverse, now remember that we use this symbol to represent the inverse of the function whose ordered pairs are the following. So this is our f. Now, graph both relations. Is the inverse of function and explain. So a relation, remember, is just is a set of coordinates drawn on a grid. Now, is the f a function? Let's check. What makes coordinates a function? Well, that is if the x values, the same x value has different y values. So for every x, there can only be one y. Is that the case with these coordinates? Well, if you look at these coordinates, they have different x's. So we don't have to worry about it. It automatically means that this must be a function because it's just a list of coordinates. Now, will the inverse be a function? Well, let's check out the inverse. The inverse will be the reverse of the coordinates. So these are the coordinates, we reverse them, and this is what we get. Do it again for the second one, the third one, the fourth one, and the fifth one. And what do you notice? Well, let's look at why we circled these two. First of all, looking at this, what makes this a function? Well, for every x, there can only be one y. Is it true here? Well, these two have the same x. But look at the y values. They're different. So here, it's telling us that for every x, there can only be one y value. And in this case, the inverse is not a function because when x equals 1, there are two y values. So the definition of an inverse is that for every x, there can only be one y. In this case, there are two y's for the same x. So it can't be a function. Now let's look at the graph of this. So we're going to have the coordinates here. So we're going to graph it out, and we're going to graph out each point. Ready? Here it goes. Here's the first one, -2, -8, -1, 1, 0, 0, 1, 1, and 2, 8. So again, -2, -8, -1, 1, 0, 0, 1, 1, 2, 8. There we go. And now we're going to graph the inverse. Inverse is going to be at -8, -2, 1, -1, 0, 0, 1, 1, and H2. And we just graphed it green so that you could see it a little bit better. So here they are. Now, note, I want you to look at just the blue ones for just a second. With the blue ones, can you tell if this is a function? Just the blue ones? Well, yes, it's a function because all of these satisfy the vertical line test. Now, with the green ones indicate that it's a function. Let's look at the green ones. So if I drew a vertical line through here, 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 and here, do we only touch one point? Well, no, folks. Right here, we would have hit 2. So that means definitely that the inverse would not be a function. So we were able to prove that using the coordinates and by looking at the actual graph. But let's look at some more parts that are important. For example, if I drew a y equals x line, that would be this yellow dotted line here. This y equals x line, remember, is our mirror. It actually indicates where the blue and the green are reflections of each other. Let's look at the first one. For example, looking at these, on the y equals x line, we can see that the points, the coordinates, have very special features, and they are this point and this point are mirror images of each other directly across the mirror. And this point and this point are mirror images of each other. And these points here lie right on that line. We'll talk about those in a second. But finally, looking at this point and this point, they're mirror images of each other. But specifically these 2 points, okay, they're actually mirror images of each other right on top of each other. And they are special points that are found right on the mirror. And these special points are known as invariant points. Invariant points are points that don't change when you take the inverse of it. Also, something else to note is that, remember, we already saw that f was a function. What about its inverse? Do you remember what the inverse said? That's right, the inverse is not a function. Why? Well, if I drew a vertical line through those 2 green points, we found that the vertical line passes through 2 points, and those 2 points indicate that the vertical line test fails. It fails here and here, and because it fails the VLT, it is not a function. So we were able to prove it using the definition with the coordinates, and we are also able to prove it using the graph. Moving forwards. Example number 2 says, given f at x is equal to 3x plus 2, find f inverse of x. Is the inverse a function? Is it a function? Well, we need to know what the equation looks like for the inverse. So let's do that. When you do an inverse equation, what you have to do is switch the x and the y. In this case, we don't have a y, so we said y equals f at x. That's what we're making it equal. And we're going to switch out the x and the y. So instead of f at x equals, it's going to be x equals 3y plus 2. Now remember, I just wanted you to note that y is the inverse. It is not actually y, but it's the inverse. So I'm just going to highlight in a different color to remind you that we want the inverse. Okay? Next, when you switch out the x and the y, you must solve for y. You must solve for where y is now. That means get y by itself. How do we do that? Well, we're going to move x minus 2. We're going to move the plus 2 over. We're going to move the plus 2 over to get minus 2 over here. So x minus 2 is equal to 3y. We need to get y by itself, so we're now going to divide by 3. We're going to divide the whole thing by 3. What is this, guys? Let's look at the equation. Maybe let's look at the equation a little bit differently. We'll look at that in a second. This equation is actually a line. It's a line because x is on the top and the exponent on the x is 1. So it's a linear function. And that linear function indicates that, the linear equation indicates that it's a line with a certain slope. A line with any slope is always a function. So yes, the inverse here is a function because the inverse is actually a line. And if you look at it written here, guys, I just noticed here, you take out the 1/3 out, you're left with x minus 2 as the leftover, and this 1/3 would be your slope, okay, and the actual function would have 1/3 of x minus 2. And that, folks, is your inverse equation. And there we go. There's your inverse equation, 1/3 of x minus 2. Or you could write x minus 2 over 3. Both are acceptable. Moving forwards. Example number 3. For f at x equals 2x squared plus 16x plus 29. You're asked to determine the f inverse of x and graph both f at x and f inverse of x on the same graph. Why do we do that? Well, we're going to look at the reason in just a minute. First of all, we want to find the inverse equation. What kind of equation is this? That's right, it's a parabola. A parabola has to be in vertex form to get the inverse equation. Is this in vertex form? No, it is not. We need to put it in vertex form. How do we do that? Well, in order to put it in vertex form, we have to complete the square. So f at x equals 2 bracket x squared plus 8x plus 29. That is the first step because we want to make x squared have a coefficient of 1, and we remove that a value from anything that involves a variable. There it is. Next, what you're going to do is 2 bracket x plus 4. Remember, it's this number divided by 2, all squared, and then we're going to subtract the a value times the number inside squared plus 29 is the leftover right here. So now what we're going to do is simplify that k value, x plus 4 all squared, minus 3, because minus 2 times 4 squared is minus 32, plus 29 gives us minus 3. This is the equation in vertex form. Next, we have to switch y with x. So we're going to switch the x and y. Again, remember, I replaced this with y, and now we're going to switch it. So x equals 2 bracket y plus 4 all squared minus 3. When I do that, I move the minus 3 over. It becomes plus 3. So x plus 3 equals 2 bracket y plus 4 all squared. Now remember, this is not y. It is actually y inverse or f inverse. So this is going to be our f inverse right here, folks. So what do we move over? We move the minus 3 over. It becomes plus 3, exactly as such, equals 2 times y plus 4 all squared. Next, what you're going to do is divide by 2 equals y plus 4 all squared. Next, what we're going to do is take plus or minus the square root of x plus 3 over 2. Now notice the way it's written here. Please don't go into a panic. Remember that x plus 3 all over 2 is just 1/2 of x plus 3. Both of these are the same. Yes, you could have left this as x plus 3 over 2. I just wanted you to see it in different forms. Now y plus or minus, remember that when we get rid of the square, we take the square root, but we're not sure if that number was originally positive or it could have possibly been negative. So we have to have both cases. And what does that leave us? Well, that equals y plus 4. What do we do now? Well, once we have this, we can now move over. The plus 4 becomes, so we're going to move it and get plus or minus square root of 1/2 of x plus 3 minus 4 is equal to y. What is this, guys? Well, this is not really y. Remember that y is actually f inverse. So let's look at the example here. So we have plus or minus 1/2 of x plus 3 minus 4 is equal to y. That means f inverse is equal to plus or minus the root of 1/2 of x plus 3 minus 4. Okay? And we rewrite it again. And remember that it's plus or minus. So it could be the plus version of the square root of x plus 3 minus 4 or the minus version of root 1/2 of x plus 3 minus 4. So very important, it is two possible root functions. The inverse is a combination of two root functions. The inverse is a combination of two root functions. All right, and we're going to look at why it's two root functions by looking at its graph. All right, looking at the graph, here we go. So let's move forwards. Those were the coordinates that we have for a basic quadratic. Remember, a quadratic starts off in the basic form as such. Remember that this is -2, -1, 0, 1, and 2. We square each of these numbers. That's how we get this. We draw the new coordinates, which would be x minus 4 and 2y minus 3. Looking up here, these are coordinates. We calculate the new coordinates. Here they are. So we follow the rules about how to do the coordinates. Once we've done that, these are our coordinates for the original function, f at x. Now we need the inverse function. How do we find that? We have the equation, but rather than plugging it into something like this, folks, we know the coordinates of the parabola. What can we do with the coordinates in the table? That's right. What we can do is reverse the coordinates. So each of these coordinates are reversed. Once we reverse the coordinates, that gives us our inverse function. We can actually graph these points and determine the shape that it looks like. Because to be honest, it's still a parabola. the parabola just changes itself. We're going to see how the parabola changes it by looking at the graph. Ready? So we're going to have a graph, and we're given, remember those coordinates we have. So I'm just going to keep the coordinates here, and we're going to take the grid and graph these points. So the first one graphs like this. This is the F. So F looks like this, folks. These are the coordinates for F. Now, let's do the coordinates for the inverse. Here they are. These are the coordinates for the inverse over here. Notice the shape it takes. The parabola goes this way. The inverse will go this way. So the shape stays the same. The difference is it gets reflected. It gets reflected across this y equals x line. Here it is. Each of these black points has a mirror image of these blue points. So literally they are mirror images of each other if we match them across the mirror. Funny enough, in our case, the invariant points, there are none, because none of these black points, and even when I draw the curve, like so, and the curve of the blue, none of these points actually touch this y equals x line. So we're not going to have any invariant points. Also, looking at the blue and the black, look at the way they look. This one actually looks like a parabola opening up. This one looks like a parabola opening sideways. But wait a minute, we've never seen a parabola sideways. Well, folks, yes, you have. You've seen it when, for example, let's take out part. We have our f at x, just quickly, f inverse of x. And let's say, okay, so there's no invariant points, just to remind you. And it's not possible because it doesn't touch. Remember, invariant points have to actually touch this yellow line, and it doesn't. But more importantly than that, we're going to restrict the domain. So looking at just this part of the parabola, okay, so did you notice how that erased? Let me just show you. Okay, so that was originally there, and what happened is that it erased itself. So we're only looking at this part of the parabola. That means that we're only looking at this value from -4 forward. So if we talked about the domain, we're only looking at x is greater than or equal to -4. So we cut it off at the vertex. Well, that means our blue graph will be only a certain amount. So we take the domain. We're only looking at the numbers greater than or equal to -4. That is the points from the vertex, from the axis of symmetry, to the right of it. Now, what does that mean about the blue graph? Well, right now, the blue is not a function. You would agree with that because it doesn't satisfy the vertical line test. But if I take the black and say, I only want to see half of the graph. So again, the half that is less than that. So if we're looking at coordinates, it's these 3 coordinates we're looking at. Well, that means it's going to be these 3 coordinates we're going to look at on the inverse. That's right, these 3 points. Now, is the inverse a function? Well, yes, it is. What function looks like this? We've seen a function that looks like this. Yes, that's right, the root function. The root function. Let's look back at the inverse equation. Remember, the inverse equation looks like there's a positive and there was a negative root. Remember, it was 2 parts. One part was the positive root, one part was a negative root. That means the positive root matches the original basic that we talked about, the root function, earlier in this unit. The negative root function would be the one which reflected vertically and looked upside down. Well, which graph did that graph match? you should be thinking and saying, oh, that matches the positive root. And that's right, folks. It matches the positive root. If we wanted the negative root, we had to have restricted the domain differently. So let's look at a restriction of the domain of another type. So we could do like we had before. So let's go back to the other screen. Remember that we had the domain is x belongs to real such that x is greater than or equal to -4. And that was this one right here. What happens if we wanted the other one that was on this side that disappeared? Well, the inverse was the other side going downwards in that direction. That equation was the negative root that we saw earlier, the negative inverse root. Now, keep in mind, when we restrict the domain, we have to restrict it either greater than or equal to -4 or x belongs to real such that x is less than or equal to -4. So again, the domain would be restricted so it's less than. Anyways, folks, I know this was a big lesson, but the importance of this is the fact that inverses are just a reflection on that y equals x line that you see here. The inverse can be a function if you restrict the domain, but in general, we always just take the original function, whatever it is, and just switch the x and y values, and that will give us our inverse function. And remember, an inverse does not change the shape. It changes where it's located, not the shape. All right, folks. Well, that's the end of the video. Have a numerical day. Take care.